Welcome to the fifth class meeting of EECE451, Introduction to Digital Signal Processing. As usual, there will be homework and more proof show type problems will be given to you in addition to a simple programming homework problem. Probably from this homework, the topic of the programming homework may be changing. Okay, here goes the review. Last time, we started to classify so-called the discrete time systems. So we consider a mapping rule that admits the entire discrete time signal and generates another discrete time signal. Then we call this mapping rule as a DT system. Since we have defined a very big set, the set of all DT systems, without doing classification, we can't proceed any longer. So classification of some concept is actually corresponds to divide this entire set into subsets. So first, we introduce the subset of DT linear systems. And we also introduce the subset of DT time invariant systems. Of course, these are very representative subsets of the entire DT systems superset, but we can also define, for example, DT causal systems. And if you want, especially if you are doing digital signal processing to control some environment, then you may want to introduce DT stable systems. So last time, we defined what is linear and what is time invariant and what is bounded input, bounded output stable. Last time I skipped this part, so I have copied the page to define the causality. So you will soon see this definition. After we define these subclasses, we focused on the intersection of these two subsets. So our interest in this course and in many courses in electrical engineering is discrete time or continuous time, linear time invariant systems. What is so special about discrete time LTI systems is that what kind of component you use in order to actually build this system. Mathematically speaking, another associated discrete time signal called the impulse response fully characterizes a DT LTI system. By the way, what was the definition of the impulse response of a DT system, DT LTI system? The impulse response could be many depending on where you place the non-zero value. But when you talk about DT LTI system, you use the unit sample function with the non-zero value located at n equals 0. So you apply 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, and this location is your time origin. Then this LTI system will generate a sequence. That sequence, viewed as a discrete time signal, is what? The impulse response. Got it? So, very interestingly, if it is known that this system is DT LTI, you just need to apply delta of n and record h of n, the response. So the response of the system to the impulse input, that is impulse response. You now can compute any arbitrarily input signal's response by simply convolving the input signal with the impulse response. By the way, this denotes the convolution sum. And the convolution sum is not just an operation on x evaluated at some specific time and h evaluated at specific time, but what? Operations on the entire input signal and entire impulse response in this way. Suppose we use the summation variable k, then we can write the convolution sum as the product of the input and what? The impulse response delayed by k. Okay? So the convolution sum can be viewed as the delayed weighted sum of impulse responses. By changing the variable, you may rewrite this one as h summation of h of L times x of n minus L. I have intentionally changed the integration summation variable to L. You can do that, not difficult. Now, this says the output is delayed weighted sum of the input. Got it? In this way, the convolution sum satisfies so-called the commutativity, in Korean, 교환 법칙. There are many operations that satisfies commutativity, and mostly they are very interesting operations, like simple addition and scalar multiplication with another scalar. Got it? Anyway, so impulse response is very, very important. There could be many different ways to implement the same, mathematically same system, but different implementation always results in the same impulse response if the system, two systems are identical DT LTI systems. From this idea, when you really practically implement, which means that you approximate this mathematical model or vice versa. Given a practical real-world system, you approximate the real-world system by a mathematical model, a DT LTI system. You must be always careful because there could be many different ways to implement approximate a DT LTI system, but some implementation may be very vulnerable to production error or some noise or something you could not imagine. Okay? This is very important as an engineer. You always remember, this is my message in this course, you must remember that different implementations hopefully resulting in the same system, but in practice, they may behave very differently in some situations. Got it? Anyway, so we focus on DT LTI system, and impulse response is very important. So last time, I little bit gave you a preview like this. So what if a DT LTI system is causal? What if DT LTI system is BIBO stable? What can we say in terms of our impulse response? And actually, most of the electrical engineering students who took signal chain systems already know the answer. But anyway. So this is kind of a good preview, I believe. So let's go back to the previous lecture note. And here goes the causality. So suppose your DT system is not yet linear and anything. A DT system is causal. If. What does this mean? Causal. So I hinted in the last class meeting that a causal system satisfies so-called 인과율. So cause and effect. This is simply translated as 원인 and 결과 in Korean. So causal system satisfies this rule. What does that mean mathematically, given a DT system? And here, it's a kind of very vague, not precise definition of causality of a DT system. So let me give you a more formal definition. So a DT system is causal if x1 of n generates y1 of n, and x2 of n generates y2 of n. Here, the long right arrow means this is the input and that is the output to this certain DT system. Got it? So suppose you have x1 that generates y1 and x2 that generates y2, and x1 of n equals x2 of n for all n less than or equal to some certain n0. And this must imply y1 of n equals y2 of n for all n less than or equal to n0. Got it? So a DT LTI system is causal if, let's say this is A, implies this B. Got it? So this entire statement implies this statement. By the way, A is for any x1 and x2 that satisfies that one. Okay, not a single one. Okay. And you may wonder why this specifies, this precisely defines causality. Just there are two ways, just accept it. Second is that think over and over. Then no other definition is better than this. Okay. By the way, there are some consequences of causality combined with linearity or something. So suppose a DT system, DT system is linear. Then let me, I don't do that. Okay, let me skip this one. We will come back anyway. Okay, so this is the definition of causality of DT system. And let's think about some example that violates that one. So the simplest one would be this one. Of course, when we describe the input-output relation of a DT system, this must hold for all n integer. Now, if this system satisfies this statement, A implies B, and we may consider two inputs. something like this. Okay. Advance. Okay. Not this one. So this x1n and x2n are equal for all n less than or equal to 0, right? Now, what about the output? The output of the first one is what? Sorry, 0. And what about y2? So you can see that at n0, which is 0, they are different. And you may say it's obvious because the current output at time n is the future input at n plus 1. So you can interpret from this simple input-output relation that this system is not causal. But more precise way is to use definition. The problem is that you cannot just apply definition every time because it's cumbersome to find some counterexample. Fortunately, in this course, we are focusing on DT LTI system. And here goes a result. A DT LTI system is causal if and only if h of n equals 0 for all n less than 0. So amazingly, a DT LTI system is not only fully characterized by its impulse response. If you add causality by inspecting your impulse response, you can immediately find whether it's causal or not. Now let's apply the idea, this theorem, to this example. By the way, is this input-output relation gives you linear time invariant system or not? First, is this relation linear? Yes. Is this system time invariant? Yes. So what is the impulse response? So you apply impulse and find the response. So impulse response. So your output now becomes impulse response when you apply delta to the input. So this is the impulse response. And let's draw it to visualize. And when the argument is 0, delta of something is 1, which means that n equals -1. You have 1. And yeah, I know, some of you are very bored in my review of this material because I covered it already in signal intelligence systems. So in that case, I'm sorry, but some of you are not remembering or haven't yet studied. So as you see that, this is violated, right? Because at n equals -1 is non-zero. Got it? So as you see here, this theorem is very useful in order to check whether a DT LTI system is causal or not. Of course, you need to prove it. And I will skip that part because you can find it from the textbook or you can find it from any web page, okay? And even, I believe, large language models could provide you a very nice proof. So try ChatGPT or Gemini or some else asking like this. Okay, please provide me a very well-written proof about a DT LTI system is causal if and only if its impulse response satisfies blah, blah, blah. The problem is that this is hard to punch in, so we have a definition. A DT signal is causal. This is actually just for convenience, okay? Because signal itself does not cause anything. This is just for a convenient definition. If a DT signal x of n, xn equals 0 for all n negative. Got it? So by introducing this definition, we may say this one as what? The impulse response is a causal signal. Got it? But I know that, and some textbooks may hate this one because, as I told you, signal itself does not cause anything. So signal is causal where it sounds strange. So some authors do not like this. Anyway, causal system, whether it is LTI or not, causal DT system, kind of interpreted in this way. Current output is a function only of past and present inputs and possibly some non-inputs. Okay. So for example, y of n equals x of n cosine, something like this. See that? The current output is a function of current input, and of course, this is not dependent upon input, but it also affects that. So this statement may be a little bit misleading, okay? This is an example of a linear time-varying causal system. Now here goes some other examples. You will see this type of input-output relation many times today and from today. And we will name this relation, but anyway, let's see. Current output equals the current input minus past input with just 1 unit of time index, past, right? So if n is 5, this is 5, and this is 4, right? And this is called a backward difference because it's difference, but current and past is backward, okay? And this is forward difference. See that? Current output is what? The difference of 2 consecutive inputs, but this is future value, okay? And this is causal, and this is not causal. And if we, of course, we need some constraint, but if let's assume that this is an LTI system. We should be careful in stating that, but suppose this is LTI. Then what is the impulse response? Your response, impulse response equals what? Delta of n minus delta of n minus 1. So if you plot it, you have 1, -1, and all zeros. So is this signal a causal signal? Yes. So if this describes the input-output relation of a DT LTI system, impulse response is given like this, which is a causal signal. So this is causal, as I claimed. Now, what about this? impulse response equals delta of n plus 1 minus delta of n. And if you draw, what do you have? You have 1 here and negative 1 here, which is not a causal signal. So this system, if it describes the input-output relation of a DT LTI system, is not a causal system. Got it? Okay. And also, we can say something very similar to DT LTI system, which is causal. So it's very parallel to this previous theorem. A DT LTI system is BIBO stable if and only if something. And recall that this part was in terms of only of the impulse response, because we assume our interest is in this intersection of two subsets, right? So we expect this blank can be stated in terms of the impulse response. And amazingly, this part is very simple. The impulse response, whose absolute value is taken and summed over the entire time interval, is bounded. Okay? By the way, we assume h of n is real valued or complex valued. So when you take this absolute value, it becomes always non-negative. And the summation of countably infinite non-negative values is either converges or diverges to plus or positive infinity. And this means that it converges. Okay? So this converges to a finite real value, okay? Non-negative. Now, of course, we need to prove this one. And proof it can be also found from standard signal gen systems book. And the proof requires for you to prove this direct way and also the converse. And you use, there are many ways to prove, but proof by contradiction is useful. By the way, proof by contradiction is translated into Korean with Chinese characters, 귀류법. And it proves some statement by negating the conclusion and show something does not match. Okay, so you can prove it, and also again try to use large language models. What I want to say here is that actually no one will ask you to prove that one because it's too well known, and most of the LLMs will never hallucinate because there are too many correct proofs. What is important is that we are focusing mostly on DT LTI system for now, and DT LTI system is fully characterized, mathematically speaking, fully characterized by its impulse response. So whenever you intersect this intersection with other definition like causality or BIBO stability, your theorem says it could be explained in terms of the impulse response. Got it? By the way, the LTI systems are in general with memory. And this is kind of obvious from our input-output relation described by the convolution sum. As I told you, the convolution sum has two expressions. And let's take a look at this one. The current output at time n is in general not only dependent upon the input at n, it's a weighted sum of x of n plus 1 because the summation variable runs from negative to positive infinity. Xn plus 2, xn plus 3, xn minus 1. The only way for DT LTI system to be without memory, what do we have? So here goes a very simple lemma, or you can even just say that it's corollary because it's too simple. A DT LTI system is memoryless if and only if h of n, anybody, equals 0 for all n not 0. Okay? Got it? Then what happens? This summation becomes simple scaling. Where it is? The output becomes simple scaling of the input, and no other input affects the output at current time. Okay? So no memory. Got it? Again, here, we could state the property of a DT LTI memory system, memoryless system, in terms only of our impulse response. Got it? Now let's see some other examples. And here, what if the impulse response is delta of n minus some constant n sub d? Of course, this n sub d is, let's say, positive integer. Okay, so n. Then, since this is a positive integer, natural number, it's a system with delay by nd. Got it? By the way, what is the input-output relation? If we describe output as y and input as x, of course, you can approach this one like this because we know that the convolution sum with input and impulse response gives us the output. And you know this already. You may fill up this ... by using the definition of the convolution sum. What about moving average? This is sometimes called simple moving average because we may have exponentially weighted moving average. Some people exponential moving average. Well, anyway, so this simple means constant weight. Okay. So impulse response is given this way. And can you prove this? As I told you, if we have input-output relation like this, and if you assume this is LTI, then you just replace this one to H and this one to delta, and you can simply get the impulse response like this, right? And if you plot the impulse response, what happens? here is n, and non-zero, actually, value 1. Let's assume M1 and M2 are both natural numbers, which means positive integer. Now, what are the time indices of this one and that one? Which one is M1 and which one is M2 or negative M2? As you see, here you have M2, and suppose M2 is now replacing K. What does that mean? Delta of N minus M2, which is delayed up to M2, right? So this gives you this one. And you replace K by negative M1, then you have delta of N plus M1, and find the argument, find N that makes argument 0, which means that this is M1. Do you get? So substitute M and find N that makes this argument 0. Then N equals M2, which is here. Okay. So among between these two, you have all ones. So how many non-zeros do you have? This one. As you learned in high school math, whenever you sum consecutive integers from some small number to bigger number minus smaller number plus 1, right? So bigger number minus smaller number plus 1 is the number of terms, right? You've done it a lot of times in to solve high school math, right? Especially for to solve some arithmetic sequence related one. 등차 수열 문제. Okay. We've seen accumulator. Do you remember the accumulator? You sum up past n values or all the values up to now. And let's assume all the values up to now. So let's say your current output is what? This one, or yeah, something like this. Yeah. So let's take a look at the lower one. So current output is what? Summation of the current input, which is x of n, and the one time instant previous one, x of n minus 1, n minus 2, up to x of negative infinity. So the current output is a summation of all the past values and the current value. And what about this one? Same thing. Change of variable gives you current output. You substitute k equals 0 is the sum of current input, and k equals 1 means 1 time instant past. K equals 2 means 2 time instant past. So given any case, your impulse response is what? If you use the upper one, if you use lower one, and if you draw both of them, what do you have? Let's start this one. So for k equals 0, you have delta of n, delta of n minus 1, delta of n minus 2, and up to infinity. So this is the first one. What about the second one? Let's choose n less than 0. What happens? When n is less than 0, this is less than 0, and your argument of delta function can never be 0, which means all zeros. What if n equals 1? Then you have single delta of 0, which is 1. So you have 1. What if n equals 1? Then you have delta 0 and delta 1. Again, this guy is never 0, so you still have 1. Similarly, for all positive, non-negative n's, you have all ones. So they are the same, right? So there are many ways to find the impulse response given the input-output relation. For this one, we've already done, so let me skip. And there is an important definition you need to remember, and you will speak a lot after you take this course, is what? A DT LTI system has an infinite impulse response or has a finite impulse response. So you may state like this, a DT LTI system is an IIR system or has an IIR. Here, R is the response. So they are the same statement. A DT LTI system has an infinite impulse response. But be careful. This infinite, so IR means here, impulse response. But be careful. This infinite does not mean your function value is infinite. Your support is infinite. By the way, what is a support of a function? Given a function. The support of a function is defined this way. The subset of the domain of a function on which the function value is not 0. Okay? So let's see our very special function like this. So y equals x plus absolute value of x, right? You have this one. Now, what is the support of this function? The support of this function is what? X positive, okay? Because on this interval, the function is non-zero. What about this one? So in the left case, we assume that the function, let's say f, is from R into R. Okay. In that case, the support is all positive real. What if this case? Now our function f is from z to z, and the relation is the same. Now what is the support of this function? The support is what? The support is positive integer, right? In the same way, now let's take a look at our impulse response. For example, this one as an impulse response. What is the support of this impulse response as a function from z to r? The support is n equals negative m1, negative m1 plus 1, dot, 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 up to m2. Now, is this set an infinite set or a finite set? It's a finite set. So this simple moving average with finite m1 and m2 has a finite impulse response. And this system simple moving average system as a function or function as a system has what? A finite impulse response. Got it? So you have that. What about this accumulator? As you see here, what is the support of this function? All non-negative integer. Is this set a finite set or an infinite set? It's an infinite set. So this accumulator as a DT LTI system has what? Has an infinite impulse response. And this system is an IIR system. Got it? So here, finite impulse response, infinite impulse response does not relate it to the value of the function impulse response, but the support, size of the support of this impulse response. Got it? So let's test your knowledge. Suppose a DT LTI system has impulse response, which is the unit step. Now, what is the support of this function? Quickly draw the impulse response. This is what? This system is an IIR system. This system has an infinite impulse response. Got it? What about this one? Again, since suppose A is non-zero, then you have what? Due to this one, right? And this is never zero, so you have IIR system. And FIR, as I told you, finite impulse response, but as you see, finite duration or finite support. Here, this is skipped. So we've already seen that a simple moving average is an FIR system, or it has an FIR, finite impulse response. By the way, here goes our very interesting corollary. By the way, corollary is a consequence of very simple consequence of a proposition or lemma or theorem. Very simple. So this one, I would say it is a corollary because we know first statement, a DT LTI system is causal, sorry, not causal, BIBO stable, I'm sorry. If and only if impulse response is absolutely summable. So absolute value, when it is summed, is finite. And this is called absolutely summable. And here goes the definition. A DT LTI system is an FIR system if what? Impulse response has finite support. What does that mean? This summation has finite lower limit and finite upper limit. And you already know, I'm not going to prove it because it's very difficult to, as difficult as to prove 1 + 1 = 2. So any any summation of finite number of real numbers is finite. It's too obvious, right? So FIR filter, FIR DT LTI system is always BIBO stable. So sometimes in control theory, you need your system to be BIBO stable. And you design some system that always have finite impulse response. Then your system is guaranteed to be BIBO stable. So this is the way to enforce your system to be BIBO stable. Okay, this part I will skip. Here goes another definition. And this is very, very important for control engineers and communication engineers. And here goes the concept of the inverse system. First, in order to talk about this one, we need to have a system. So here is DT discrete time system. I'm not saying LTI, okay? So here is a DT system. And you have input and you have output. Now you have another system. Let's say that DT system 1 and DT system 2. And you have Z. And here was the definition. The DT system 1, sorry, this system 2 is the inverse system of the DT system 1 if, so this is definition. I'd better say W. Okay. When you cascade these two, now how many ways to cascade these two or serially interconnect these two? 2 ways. Okay. DT system 2 first and DT system 1 next, right? Whenever, which one do you choose? The output of the overall system equals the input. Okay. For every possible input X. Okay. And you may wonder, well, if this holds, this must hold, but not always. So be careful. Okay. In order to extend the definition, you need both of the interconnections. Now, here goes the lemma. Suppose these 2 systems are DT LTI. So let's consider DT LTI 1 and DT LTI 2. Now, anybody, what would be the condition for this system to be the inverse system of that one? So if we just use the definition, the cascade of these two must be an identity system. What does that mean? DT LTI system interconnected is a DT LTI system by the convolution, associativity of the convolution, right? So this has impulse response H1, and that has impulse response H2, and overall must be identity. So if this holds, right, we are done because the convolution sum is commutative. So this one holds, that one holds. Got it? So many results can be stated in terms of impulse responses. Got it? Now, let's see an accumulator that sums up all the past and current values to generate the current output. And suppose you have a backward difference system. Let me recall you that the input-output relation is given that way. Okay. These two are inverse systems. How can you prove? There are many ways to prove. You may substitute this one to somewhere in accumulation formula. But the simplest way is to use the impulse responses, because h1 of n equals what? Summation k from negative infinity to 0 delta of n minus k. Sorry, this is not correct. N delta of k. And this h2 is simply delta of n minus delta of n minus. So by computing the convolution of these two impulse responses, you just need to show that the convolution gives you delta of n. If this is too difficult, then there is another way. So you try. You can easily show that one. And actually, this one is same as u of n, as you've seen. So just compute that one. It's another way. Okay. Here comes most confusing, one of the most confusing terminology, LCCDE. By the way, here L means linear, C means constant, another C means coefficient, D means difference, E means equation. By the way, in signals and systems, you've seen something different. D was differential for continuous time systems theory. Fortunately, here we only talk about LCCDE when D means difference. In Korean, 선형, 상수계수, 차분, 방정식 is one way of translating this one. By the way, be careful. This Oppenheim, the former MIT professor, loves this terminology LCCDE. But some textbooks never use this one. So be careful. Some textbooks never say LCCDE. They use some different terminology. But anyway, I was taught using the Oppenheim's signals and systems and also DSP, so I'm just got acquainted with LCCDE. And what does this mean? Similar to a differential equation, you have, suppose, two signals, say x and y. But here we are handling a discrete time, two discrete time signals. So on the left-hand side of the equation, you only have y of n minus k's. And this right-hand side, you only have x of n minus l's. Got it? And this not only holds for specific n, this must hold for all n. In addition to this one, you have what? Linearity and constancy of coefficient. So here goes something like this. I believe left-hand side has A and right-hand side has Y. Yeah? A, B, let me see, K and M. Okay, K and M. So this is a general form of a linear constant coefficient difference equation. It's linear because you have linear combination of outputs and linear combination of inputs on both sides. And also, here constant coefficients means that this is constant. For what? For all n. Okay. This does not change. And also, that does not change if you change this n. Got it? So suppose you have something like this. Counter example. Suppose you have cosine n y, sorry, k, n minus k equals m sine something like that. Is it an LCCDE? No. Even though the left-hand side is a linear fixed n, okay? Fixed n, and just look at that. It's a linear combination of outputs. However, when you change n, as I told you, what does this mean? You have countably infinite equalities. And when you change index, does this change? Just a second. Let me see. I'm sorry. NK. N M. Sorry. Does this change? Yes. Okay. When you change n, this coefficient changes, and that coefficient also changes. Of course, either one is changing, then you cannot say constant coefficient. Constant means when you change n, okay, it's okay. It changes for k, it changes for m. It doesn't matter. Okay? Why this LCCD is so important? Because there are many ways to describe the input-output relation of a DT LTI system. Fortunately, some, I'm not saying all, okay, some, this is very important, okay, some DT LTI systems can be well described by LCCDs. Okay. This is very important. The problem is that here, the most general form has what? Countably infinite terms and possibly countably infinite terms. However, in a restricted form of LCCD, people allows only finite summations. Okay. So depending on the textbook, depending on the authors, some people say this is not LCCDE if you have either one of the side has infinite terms. But, well, I don't like that, okay? So anyway, let me just use countably infinite general form. And you may say that, okay, it's so general, so this must be changed to all. Still no, okay? Still no. Some DT LTI systems, it's very hard to be represented by LCCD. So be careful. Some DT systems can be well described. And you may say that, okay, so professor says LCCDE has some limitation in handling DT LTI systems. Yes, I'm saying that LCCD is not omni-powerful, okay? It's not fully powerful, but it's very, very powerful because Anyway, we engineers build approximate systems. Okay? We have mathematical model we want to implement. However, we never precisely implement it. So anyway, if you have a very good tool to well approximate some system, and that tool is very simple to use, it's good. For example, when I was a graduate student, my seniors always advised me, hey, Junho, never do any research related to nonlinear systems. You will never graduate. So I try to avoid nonlinear systems. Now, you all know that simple neural nets have nonlinearities, right? Now, what happened? People have found some nonlinear systems, for example, feed-forward neural nets or some variations. They are now very easily so-called trained to approximate some nonlinear system. So the world is changed. Okay? So as far as you use neural net. Of course, neural net is not, how to say it, it's not applicable to all problems. However, there are many problems. Before, it was hard to tackle, but now it can be solved, not perfectly, but very, very engineering sense, very, very good sense to be solved using this nonlinear neural nets. Okay? So in that way, same. Linear constant coefficient difference equation is a very, very powerful tool. Even you have some cases that is not good. Got it? So it has limitation, but it's very, very good. Now, here goes the tricky part. Here goes the question. Suppose a DT system has input-output relation. Let me briefly write I/O relation given by an LCCDE. Now here goes the question. Is this DT system linear? Many of you may regard this question stupid because input-output relation is completely linear relation. How can a DT system described by an LCCD can be some nonlinear system? And unfortunately, the answer is not always. Why? You've already seen from your differential equations course. Sometimes, depending on the, for example, initial conditions or boundary conditions, you have your solution to a differential equation, summation of homogeneous solution and particular solution. What does that mean by homogeneous solution? It is due to what? Initial condition or boundary condition. And here goes some simple stupid question. Is this relation linear? Yes. Is this relation linear? Actually, this is not linear. Even though we say this is linear equation. This is, precisely speaking, is an affine relation. Or some people say affine linear, but I really hate that. Okay? Because linearity requires what? Zero input, zero output. Why? Because if you multiply any number to zero, it's zero. So due to linearity, your system, if it is linear, must satisfy 0 input, 0 output. And this one has non-zero output when input is 0. So precisely speaking, y equals 5x plus 1 is not a linear relation, even though we usually say it's a linear equation, linear relation. Precisely speaking, it's not linear. Something similar is happening here. Even though we are given an input-output relation over DT system in terms of a linear constant coefficient difference equation, depending on the initial condition, you may have non-zero output to 0 input. So it's not linear. Got it? So be careful. However, here goes interesting thing. So you have the same thing. And in addition, the DT system satisfies 0 input, 0 output. So you apply all 0 signal to a DT system described whose I/O relation described by LCCDE. So input is all 0. And you find output is an all 0 signal. Then this DT system is LTI. So it's not only a linear system, it's time invariant system. So, and you want to ask why, and as I told you, just look up your signal gen systems or ask your LLM, because this is so famous. Okay? And this statement is just the same as linear constant coefficient differential equation case. Got it? And now suppose this A0 for Y0, right? So sorry, Yn, so K is 0, right? Is non-zero. Then from left-hand side, you can subtract all the other terms, which means you usually say move all the other terms to the right-hand side, negating the sign. We have the current output. This is current output at time at. Is now rewritten as a linear combination of all the outputs and all the inputs, right? And this is one way. Another way to rewrite an LCCDE. So sometimes your LCCDE is given in this form or in that form. But both are in the form of LCCDE. Now, let's go back to our friendly accumulator. And here, y of n equals, and you have summation k from negative infinity to n x of k. By the way, is this in the exact form of LCCDE? No, because we must have something like this, not this one. So we may use another relation, equivalent relation.
Dr. Joe.
Now, your output is what? This linear combination of all the outputs is 0. However, you have linear combination of all the inputs. So this is the LCCDE, right? Accumulate. Yeah. And another one is that we can rewrite that one as sum of x of n plus that one and see this relation and replace that one as y of n minus 1. And here goes something strange. So this one is LCCDE for accumulator, and that is also LCCDE for an accumulator. Which one is correct? if we define LCCDE that can have countably infinite terms, both of the expressions are correct. However, as I told you, some researchers restrict their LCCDE to have finite number of terms. Now, is this have finite number of terms? No. So for those researchers or book writers, this is wrong, and that is correct. Got it? So sometimes, remember from this example, sometimes you may have input-output relation of a DT system involving infinite terms, but rewriting that one, there could be a way to have finite terms without modifying the input-output relation. Got it? And with finite number of terms, what would be good? Actually, you will see implementation of a DT LTI system by directly using LCCDE. In that case, this delays actually is related to a delay component. Each delay requires one delay component. Now, can you have countably infinite delay components in your implementation? No. That's why some people just, hey, let's forget LCCDE must have finite terms. In that case, they significantly reduce its applicability. However, when we want to implement it, it's very easy. We have always finite number of delay components. Got it? Anyway, so let's stop here and continue next discussions next week. Okay, that's all for the day.